In 1981, I encountered a problem with the bisection method of finding roots of continuous functions. So I thought I'd look at what is happening now. Because AI is trained on the current state of the subject, it would be interesting to see what they thought about my problem, and here's what 7 of them gave as responses to my query. I have marked bad concepts in red, problematic concepts in orange, and good concepts in green. So here's the first one, ChatGPT, where I ask, can you give me a Python function for finding the root of a function using the bisection method? And it responded with the following. I am not going to read the program, but let you have a look to see what it says, and basically notice that I have made some annotations on it. The orange indicates it is not the greatest. The red indicates it's a really bad suggestion. Now you will notice that there's quite a bit of red, some orange, no green. But it did mention the relative error, and that will be important later on. Then I tried it with Claude, and it gave a rather similar type of program. A lot of comments, which is good. But again, we're seeing that red is showing up along with orange. Quite a bit of red, in fact. And it does a bit of explaining as to what has happened. You'll notice that there's a comment here about a verbose function. I clipped that out because all it does is print out the steps that we're going through. CoPilot. Does it do any better? Well, there's some orange and there's some red, and so again we're seeing a lot of red and orange. What about Gemini? Again, it explains what about its parameters. And there's orange and red and more red. And again, it explains what the function is supposed to accomplish, which is actually a fairly accurate description of what one wants to do with the bisection method, except for numbers 5 and 7. But we will be looking at that detail later on. And it also gives an example of how you can use the function. What about Grok? Very similar in many respects. Some orange shows up, and there's red again, but not quite as much red in Grok. What about Meta? Seems to like the idea that we're using a numerical method. Some orange, some green. Not so much red, which is rather interesting. Then Perplexity. And you notice it indicates that it has reviewed 15 sources, and again it describes what it is doing. Some orange. Okay, we got some green here, but some more red. And it also gives an example. The bisection method is really a means of finding an approximation to the root of a continuous function. and continuous is very important. It is typically labeled as slow but sure. Of course, it's only sure if it gives the right answer. So let's see how our AI programs make out. And the process is very simple. We find an interval which contains a root, and then we proceed to bisect the interval and all successive intervals which contain that root until we get a good approximation. At this point, I'm not saying what good actually means. The problem is not in doing the bisection, but knowing when to quit. A fairly standard set of possible stopping conditions is given by Burden and Fares, most recently in their 10th edition, but it's been that way in most of the previous editions. 2.1 is an absolute difference, 2.2 is a relative difference, and 2.3 is the absolute value of the function. An interesting thing is that while Burden and Fares suggest that 2.2 is probably the best, they use 2.1 in their algorithm. All the AIs use 2.3 and or 2.1 as a stopping condition. None of them use 2.2, the relative difference. So let's see how this works out. Okay, the first thing I indicated as a bad condition is the absolute value of the function being less than a tolerance. And ChatGPT, CoPilot, Gemini, Grok, and Claude all use this as one of its stopping conditions, and I've indicated what they have used as their tolerance in each case. Now, let's take a look at what would happen if we have a flat function such as f of x equals 10 to the minus 20 times x. Take a to be a large negative number, minus 2 times 10 to the 10th, and b to be a rather small positive number, 0.0001. These will, in fact, enclose the root at the origin. Our first step is to bisect the interval. When we do that, we get that c is going to be equal to this number, minus 999, etc., 0.99995. So the absolute value of the function is going to be 9.999 times 10 to the minus 11, which is less than 1 times 10 to the minus 10. So that satisfies the potential stopping condition. On the other hand, if we let a be equal to a small negative number and b be a very large positive number, we get a similar type of thing. And we find that the magnitude is going to again be less than our tolerance. And that means that, depending on our choice of a and b, we can show that the root of our function can be anywhere in the interval shown here. And I'm not going to read the whole thing off because we can see that it is a very large interval, and hence we have a ridiculous result. Claude also uses this to ensure that the endpoints of the interval are not roots, but for a flat function, this will be a problem, as we will see. Almost all the AIs use the absolute difference stopping condition, although Gemini doesn't divide by 2. This is not surprising, as most textbooks, as well as other sources, use this condition. Well, let's try the AI codes on a very simple linear function with a large root. And the function we'll take is f of x equals x minus r, where r is our root. And I've given the root here. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 0.12, etc. And a tolerance is 10 to the minus 10. So here is our function f with function value x minus r. And I've taken a and b to just be on either side of the root. When I try this with all our AIs, they all give the same answer, and it looks like a pretty good answer, but we have to keep in mind what the absolute difference means. The absolute difference represents differences in decimal places, and in this case, the tolerance is 10 to the minus 10, and that indicates that the difference should be no more than 1 in the 10th decimal place. The problem is the result has only 7 decimal places. Why does the program return this value and not go for the full 10 decimal places? The answer, of course, is computer arithmetic. The common standard used is the IEEE 754, and the most digits that we can expect in a computation will be about 15 or 16. And we actually have that many digits, but we haven't been able to achieve the correct number of decimal places. When we do our iterations, we end up with the point at which C has the hexadecimal representation that I've shown here. It turns out that that is the same as the hexadecimal representation of our root. The reason for this, of course, is that computer arithmetic can only handle at most about 16 figures. That means that we cannot solve problems that have large roots and require very small tolerance. On the other hand, suppose we consider a very simple linear function with a small root. So in this case, we have f of x equals x minus r, and our r is 1.234, so forth, times 10 to the minus 20. That is, it's a small root, and again the tolerance is 10 to the minus 10. So here's our function, and we'll take a to be 0 and b to be 1, which certainly encloses the root. And here's what we get from all 7 AIs. Claude has a slightly different answer, but they all give results nowhere near the actual root. Claude has a code at the start that checks to see if the absolute value of f of a is less than the tolerance and returns a. In this instance, the absolute value of f of a is 1.23, so forth, times 10 to the minus 20, which is certainly less than the tolerance. This is the type of problem that I encountered the first time I prepared notes for the bisection method in 1981. When I looked at the answer I got, I thought I must have made a mistake in the code, but after careful analysis, I realized the problem was not in my code, but in the algorithm which used the absolute difference. As mentioned previously, an absolute difference with tolerance 10 to the minus 10 is supposed to produce a solution with an error of at most 1 in the 10th decimal place. But with the R value that we're using, all the digits up to the 10th place and beyond are all zeros, so we actually get no non-zero digits of information. The reason the bisection method has stopped is that it continually subdivides an interval until after 33 iterations, a stays the same and b will be equal to 1 over 2 to the 33, which is 1.164, etc., times 10 to the minus 10. And half of that, b minus a, is the value that all the AIs return as a value. This bothered me because I thought I must have picked the wrong textbook for the course. But then I went to the library and looked at other textbooks and found out that they all used the same absolute difference. Not one of the textbooks that I looked at then or since has used an example that had a root that was small. In fact, these examples typically had a root that was in an interval from 1 to 10. Take a look at the examples from the AIs. We see that 2 of the 3 stopping criteria suggested by Burden and Fairs have significant problems, even though they seem to be favored in almost all sources. In almost every source that I've looked at, the goal is usually stated as finding an approximation to the root, but it's usually quite vague on what kind of approximation is acceptable. It seemed to me, back in 1981, that to approximate one number to another should involve comparing significant digits, not decimal places, and that meant using the relative difference method. That went against what every textbook at that time was doing, and as is apparent from my AI query, they still do. Even though all the AIs have ignored it, Perhaps it is time to have a look at the relative error condition. Again, referring back to Burden and Fares, which is a standardly cited text, we have the following definition that shows how significant digits and relative difference are related. The number p star is said to approximate p to t significant digits or figures if t is the largest non-negative integer for which the absolute value of p minus p star divided by p is less than or equal to 5 times 10 to the minus t. In terms of r variables, the absolute value of r minus c divided by c is less than or equal to 5 times 10 to the minus t. Now, to avoid dividing by a small c, it's probably better to write this as absolute value of r minus c is less than or equal to 5 times 10 to the minus t times the absolute value of c. We do not know the value of r, but because both r and c are in the interval ab, the absolute value of r minus c must be less than or equal to the absolute value of b minus a. So, if we know the width of the interval, b minus a is less than or equal to 5 times 10 to the minus t times the absolute value of c, then we also know that r minus c must be less than or equal to 5 times 10 to the minus t times the absolute value of c. I asked the AIs why they have used the stopping criteria of the absolute value of the function being less than or equal to the tolerance, and or the absolute difference rather than using the relative error, and I'm going to include a few typical responses. Here is what CoPilot had to say about it. It says it is not arbitrary. It reflects what you want to guarantee about the quality of the approximation. I am not quite sure what quality they are referring to. So it starts telling me about the absolute versus relative error, and it gives as an example that if the true root is 0.001 and tolerance is 10 to the minus 6, then the tolerance times the absolute value of c might be much stricter than most users intend. But if you look at a slightly different case, if the root is the value that I've shown here, and the tolerance is 10 to the minus 6, you get no information because all 6 decimal places are 0. On the other hand, the relative error will give the correct result. Let's take a look at what it means by, but it has a weakness if the root is near 0. The absolute value of c is so tiny that the right-hand side becomes tiny too. Yes, it probably will. That forces the algorithm to continue far longer than necessary. Well, actually, the relative error algorithm will continue until you get the number of digits that you want, and I don't think that that is far longer than necessary. And then it tells us that the bisection guarantees absolute error. Well, that is not a good guarantee because we've seen that it can give unusable answers. And it states that bisection guarantees absolute error. Of course it does, because if we use the absolute error as a termination condition, then you are going to get the absolute error. It's simple, predictable, and here I also agree, and I predict that it will fail for most small roots. For some reason, it decides that it's a good idea to check for the absolute value of the function being less than a tolerance. Why would I want that? I don't want to know how small the function is. I want to know where the root is. And as we've seen, there's no correlation between those two values, unless the slope of the function at the root is in the neighborhood of 1. And I like this. It gives an early exit when the function value is already good enough. Yeah, and when the function is flat, it guarantees bad approximations. Then they try to convince me why I should rely on the absolute error. It tells me relative error fails near zero. Now I find that everyone says that it fails near zero, but nobody ever bothers to show what that failure actually looks like. And again, the relative error doesn't align with Bisection's theoretical guarantee. Who put that guarantee on it? I would think the guarantee would be that it gives the correct answer. And it can stop too early for roots far from zero. No, it will stop exactly when you want it to stop, as we see later. So the bottom line is simple. Yeah, but it gives terrible results. Okay, let's take a look at what Gemini thinks about it. Again, absolute tolerance is the simple way, and it gives the pros and cons. These are the same things they've indicated before about the relative error. Cons: it can fail if the root is zero, if the midpoint is zero, the right side becomes zero, and the condition might never be met. This, as it turns out, is wrong. Then it introduces a new concept, and it tells us that this is the gold standard stopping condition. It is used by professional numerical libraries like SciPy or MATLAB. I haven't seen the MATLAB one, but we'll see that SciPy is a different situation completely. It also makes reference here to the diagram indicating something about the granularity of floating point numbers, but it doesn't actually give the diagram. So it asked if I wanted it to rewrite the program. I thought it would be nice to see just how it set things up now. It claims that it produces a more numerically stable result than taking the a plus b divided by 2, and it tells us that it is more numerically stable, and again, if the root is near zero, the atoll dominates, preventing the code from trying to reach infinite relative precision. It doesn't try to reach infinite precision, it tries to reach good relative precision, but the atoll means that you will get terrible answers. I do not consider what they have given as a gold standard, and we're going to see that shortly. The reason that I really wanted to talk about this code is that it discusses the concept of numerical stability. Instead of using a plus b divided by 2, the AI decided to use a plus b minus a divided by 2 because if a and b are very large but close together, the first method can actually result in a midpoint outside the interval due to rounding. Then it also introduces the hybrid stopping condition because that is really the best way to do it. The stability concept is actually the main reason I included this response from Gemini. I wasn't going to until I noticed what it said about stability. As I looked over a lot of examples of the bisection method, I kept seeing that a plus b over 2 might produce a problem if a and b are very large and close together. This might happen, but for some reason nobody seems to consider what will happen if a and b have opposite signs and their magnitudes are large but close together. This is a similar thing to what's going on with the hybrid stopping condition, in that there's a potential problem and that problem has been seen, but the solution to that problem can be just as bad or in some situations even worse. So I asked Gemini about this, and it realizes that it made a mistake, so it comes up with a safer, a bulletproof midpoint calculation. Next, we'll have a look at what ChatGPT tells us and see if you can see much difference. Again, it says pure relative error fails at or near zero, and says that the relative error is fine only if the absolute value of C is not small, and it gives a pathology. And that pathology is going to be fun to deal with, because it tells us that if the true root is R equals 0, then C will tend towards 0. And that means the right-hand side of tall times the magnitude of c will tend to 0, and the test can never be satisfied in finite arithmetic unless b equals a. The problem is that they didn't take into account something that needs to be considered. So let's see what they didn't take into account. So remember, there were some green points, and this is one of them. The green point is what happens if f of c is equal to 0. Well, I'm going to take a look at this from a different perspective. I pointed out to ChatGPT that using the magnitude of the function less than the tolerance was an inappropriate stopping condition. It apologized, as they usually do, and gave us a safer variant. Not that the safer variant is all that great. But this is what they produced, and you'll notice, if you take a look at it, it's now got a stopping condition of b minus a divided by 2 being less than or equal to the maximum of a tall, or r tall times the absolute value of c. Introduce this new type of stopping condition that Gemini had. They are not quite the same, but for small c they are equivalent. At this point I have a question. Why were we not given this as a stopping condition at the start? I asked for a program to compute the bisection method. Why did it not use this as a stopping condition rather than the ones that they used? Then I pressed the other AIs, and all of them, except for Meta, came up with a version of this as a stopping condition. And guess what Meta said? That the relative error condition is actually a more robust stopping condition, especially when dealing with functions that have roots that are very large or very small values. Not exactly what the others were telling us, is it? Now let's see if this new stopping condition solves the pathology of the problem of f of 0 equals 0. Remember, that's what we were told in the pathology, that if the root is at 0, then the magnitude of c will approach 0, and that will be terrible. So I'm going to take a very simple function, f of x equals x, and that does in fact have f of 0 equals 0. So I used that new ChatGPT code with this new stopping condition, and I ran it, and look what happened. In the column on the left side, I note when f of a times f of c is less than 0. Now we start off with a equals minus 100, b equals 300, and we get to the second iteration, we find c is 0. So at that point f of c is also equal to 0. Now what happens here if you take f of a times f of c? It won't be less than 0, it will be exactly 0. And that is where things start to fall apart completely. Because we now set a equal to c equal to 0, the root is at a. That means that we have set the root at the left endpoint, and we no longer have a root in our interval. Eventually, the width of the interval gets so small that it satisfies the stopping condition, even though the root is no longer in our interval. It does not appear that our new stopping condition will solve the problem of what happens when f of c equals f of 0 equals 0. Now there's another thing that we need to keep in mind, and it may not be obvious, and that is that even if f of c is equal to 0, it does not mean that c is the exact value of the root, or in fact, very close to it. Suppose that we have a function f of x equals x minus 1.2345, etc., times 10 to the minus 70, then it's all raised to the 5th power. Then, if we take the value x equal to 1.2 times 10 to the minus 70, we get that f of x is minus 493.5877, etc., times 10 to the minus 360. Again, the smallest number that can be represented in the IEEE floating point is 10 to the minus 324, so this has underflowed to 0, and hence will return that f of x is equal to 0, even though c has just the first two digits of the correct root. Even so, we must test for f of c equal to 0. Now, suppose that we replace that gold standard stopping condition with the relative error stopping condition that I suggested. Well, with the relative error stopping condition, we take a look to see if the value of the function is equal to 0, because if the value of the function is equal to 0, then we note that the root is around c. Otherwise, we look at b minus a less than the relative tolerance times the absolute value of c and return the value. Now we try the same bisection problem using the relative error stopping condition rather than the hybrid stopping condition, and we find that it returns the correct value of 0. So again, returning to the pathology that says if b minus a is less than or equal to the tolerance times the magnitude of c, then if the true root is 0 and c tends to 0, the right-hand side tall times the absolute value of c tends to 0, so the test can never be satisfied in finite arithmetic unless b equals a. Well, yes it can, because you test for f of c equal to 0. So the pathology is actually incorrect, but what happened here is the program did not test for f of c equals 0. And so, in that case, iterations continue until the interval is sufficiently small, even though it does not contain the root. And this is where a problem arises that these programs have all missed. We need this stopping condition of f of c equal to 0, and only Meta and Perplexity even look at that as a possible condition. Now, another aspect that we saw was that the absolute value of f of c less than the tolerance would produce a terrible result for functions that are flat near the root and should be avoided because this is a bad test for finding the root. But it turns out that it does act as a backdoor means of testing that f of c is equal to 0. For some reason, all the textbooks, lecture notes, and videos seem to be very concerned with the possibility that f of c might be equal to 0 when c equals 0, but they do not seem to worry about the problem of multiplying f of c times f of a to determine the interval in which the root will lie. We have also been told that if there's a slight possibility that the true root might be 0, we should reject the relative stopping condition. I have previously shown that the absolute stopping condition is guaranteed to give terrible results for small values of the root. It seems to be the general wisdom to reject something because it might possibly present a problem at 0 in favor of a process that is guaranteed to produce terrible results over a wide range of values. This makes no sense. Now this is where the fun begins, because this comes after the previous ChatGPT session and follows the pathology, and it tells us why it used this gold standard hybrid stopping condition and how wonderful it is, and it's a standard, well-posed approach, and it has all these marvelous characteristics, and the pattern is used in essentially all robust solvers, and it cites as examples SciPy, Optimize, and MATLAB. And here is SciPy's bisection algorithm documentation. And this is what it says. It gives the absolute and relative stopping tolerances, and it tells us about the parameters. Now, among the things it does mention here is for xtol and rtol, it talks about the computed root will satisfy np dot is close. Okay, so we have to dig a little bit deeper to find out just what this in-close function is. And here it is. Now, as we read through it, we discover a warning. It says the default atol is not appropriate for comparing numbers with magnitudes much smaller than 1. Well, that's exactly where the relative error works best. It indicates that it uses the absolute value a minus b less than or equal to a tall plus the absolute value of c times r tall rather than using the maximum. But it's really the effect is the same in both cases. Remember that the pathology told us that we can't use the relative error because it's problems, so it says as a result we should use a hybrid method because this ensures a finite termination for all roots and a couple of other things, and that it's used in SciPy Optimize, but it says that the default atol is not appropriate for comparing numbers with magnitudes much smaller than 1. To sum up, because the relative error doesn't work well near 0, we should use the hybrid method, which doesn't work well for roots less than 1. To me, that's a distinct problem with logic. Now, on a personal note, I submitted a bug report stating that I was getting incorrect results for very small roots, and this led to a long discussion in which the maintainers talked about changing the documentation while I was talking about changing the program itself, and after some time the discussion ended. As I was putting this together, I went back and looked at the documentation and found that between versions 1.15.0 and 1.16.0 there had been a modification. It added a note, and guess what that note says? It says that care should be taken to select xtol for the use case at hand. Setting xtol equal to 5 times 10 to the minus 324, the smallest subnormal number, would ensure the highest level of accuracy. And guess what? The xtol value that is expressed in the note was what I suggested to them, and we're going to look at where it comes from a little bit later on. Now, this is the end of ChatGPT's response from above, and the bottom line contains a complete and utter lack of meaningful information and says, ill-posed near 0. No, it's not. Can prevent termination. No, it can't. This new hybrid method is well defined everywhere. No, not for small roots. It's consistent with the bisection error bounds. Only if you define them that way, and standard numerical analysis practice, and that is a real problem. Now I should note that it mentions a previous reference to burden and fares. I had actually queried ChatGPT about this matter on a previous thread. It seemed to remember burden and fares, but forgot a lot of the other stuff. Then I thought that it would be interesting to find out what the AIs thought that a good approximation would be. So I asked Grok, if I have a function with a root 1.23456, etc., times 10 to the minus 100, and I don't have any idea where it is, what would you consider to be a good approximation to this root? And so it tells me that a good approximation would be between 10 to the minus 108 and 10 to the minus 92. Would you accept anything in that range? This has to be one of the most ridiculous things I have seen. I have marked some of the weird comments, but I'm not going to try reading it as it's just basic garbage. Then it comes up with practical rules of thumb people actually use and concrete examples of what they would expect, which is nonsense because you should expect 15 digits. And then it gives its personal recommendations. I am not really sure what I can say about this because it shows a complete and utter lack of knowledge about how computer arithmetic works, and I really have trouble figuring out what it is trying to say. But to suggest that any number between 10 to the minus 108 and 10 to the minus 92 would be a good approximation is ridiculous. There is a simple answer to the problem. A good approximation is one that has as many digits as long as it's less than around 15, as you require. Now there's a missing check in all but 2 codes. ChatGPT, CoPilot, Grok, Meta, and Perplexity all use B-A, but they do not check to see if B is greater than A. That test should be there. Another of my orange markups, and everybody does it, they take the product of f of A times f of B, or the product of f of A times f of C. That's what all the AIs do. But what happens if f of A or f of B is equal to 0? That's when things go wrong, as we already have seen in the case of f of C equals 0 earlier on. Even if they are both non-zero, maybe f of B and f of A are large, so the product could overflow. On the other hand, if they're small, and this is the more likely case, you could have underflow. But we really don't need to do the multiplication. What we need to do is compare the signs, and that can be done simply by getting the sign of f of A and calling that the left sign, and from there on that value will never change, and we can just do the comparisons with the sign of f of B and later on f of C. You will notice that I'm not using exceptions here because it really isn't something that's unexpected. This is the kind of thing that you might expect to happen. So I suggest returning a value of not a number and say that we use 0 iterations and give the reason for stopping was that we had the same signs. This means that when we look at what is returned from the function, we have explicit information as to why we returned. Later in the code, they multiply f of A times f of C, and we saw the danger of that earlier on. It's much better just to compare the left sign to the sign of f of C. Something else that I had marked in red, and 3 of the AIs did it, there's no need to update f of A or f of D because we're not concerned with their values. What we're concerned with is the sign at the left end of the interval, and that's all we really need. So now let's take a look at where all this has led us and do a rather simple mental exercise. If you don't have a computer, then you'd have to take a pencil or a pen and some paper, and you just keep doing the computations and to get the value that you think is good enough. And that would be when the difference between A and B is sufficiently small. The problem is, what do we mean by sufficiently small? We have looked at this, and I certainly think that it's sufficiently small when the relative error is small. Now, if you're doing this by hand, you can just keep doing the bisections until you get to that value. But with a computer, there are only a finite number of numbers available, and so at some point the interval will be so small that you're not going to be able to do any further bisections. That will occur when the width of the interval reaches the minimum subnormal, and its hexadecimal representation is as shown here. You can see that all bits are 0 except for the last bit, which is a 1. We also have its representation in decimal. This means that we're going to have to stop if B minus A is less than 5 times 10 to the minus 324. We can return the approximation, the number of iterations, and a flag saying that we hit the minimum subnormal, and that is what SciPy's bisection method had in that new note. This is an excerpt from my conversation with the maintainers of SciPy. I pointed out to them one of 2 things must happen. We reach a point at which f of C is equal to 0, we have a root, or else the interval can no longer be bisected. I suggested that means setting xtol equal to 4.94, etc., times 10 to the minus 324. But 5 times 10 to the minus 324 is a good value. So let us use this on the example that caused Grok so much trouble. The default terminating condition for the hybrid gold standard method uses the absolute value of x minus x naught, and we can actually split this into two pieces. I prefer not to have two different terminating conditions in the same statement. So now we can use if the absolute value of x minus x naught is less than or equal to r tall times the absolute value of x naught, we return the value x naught. Or if it's the absolute error condition that's met, then we can return x naught as well. So optimize bisect with the default parameters, the default terminating condition, returns the value of 1.8189, etc. times 10 to the minus 12 as an approximation to a number that's 10 to the minus 100. That's quite bad, but it meets the termination condition. Suppose we make the modification suggested in the note, and now we would have that we would test for the absolute value of x minus x naught less than 5 times 10 to the minus 324 and return x naught. Otherwise, we return x naught using the relative error. And here we use exactly the same function call, except for specifying x tall is going to be equal to 5 times 10 to the minus 324. And guess what we get? We get our 15 digits of accuracy. And what have we done? We have, in fact, used the relative error condition, which we have been told time and again just won't work. Now, one of the things I found rather funny, all the AIs seem to think that this hybrid stopping condition was the gold standard of stopping condition, and they reference its use by SciPy, but they didn't dig deeply enough into the documentation to realize its limitations. And one of them even referenced my bug report about the problem. What all this tells us is that iterations can and should terminate with one of three conditions: that the function f of c is equal to 0, that the width of the interval is less than the minimum subnormal, or that we satisfy the relative error condition where t is less than about 15. While the bisection method is usually described as slow but sure, it does have an advantage over other techniques because we are able to determine the number of digits of accuracy that we have even when the program does not terminate with our required accuracy. We have seen that if b minus a is less than or equal to 5 times 10 to the minus t times the magnitude of c, then we have t significant digits. On the other hand, if we solve this expression for t, we can determine the number of digits that we have, even if we stop for some reason other than having achieved tolerance. An example of this would be f of c equals 0, and sometimes that will be a problem in that we do not have sufficient digits. So solving this for t, we get that it's equal to minus log to the base 10 of b minus a over 5 times the magnitude of c. So now we're in a position to produce code for the bisection method that eliminates all of these flaws that we have seen. So here's the program. As usual, we have a description of what the variables are, and then we start testing some things. For instance, we make sure that b is greater than a, we make sure that a and b aren't equal, and we make sure that neither endpoint is a root. Then we set up our left sign and make sure that there are opposite signs at our endpoints. Then we start the iterations. As suggested, we're going to make sure there's no possibility of overflow, although it's probably unlikely. Then we check f of c equals 0, and if it is, we compute the number of significant digits that we have. We are going to test to see if we've satisfied our relative error condition, and we're going to test to see if we are less than the bound. And we find which half of the interval C is in by comparing the left sign and the sign of C. In every instance, we're going to compute the number of significant digits, and that will give us our code. As mentioned, most textbooks seem to do one example, and the root ends up in the interval from 1 to 10. And in that interval, the absolute and relative errors are approximately the same. So let's take a look at how my version behaves in a variety of circumstances. The first one is A equals B, and as it doesn't matter what A and B are, I have chosen 1. The response is that A equals B, and it returns not a number. For the next one, the interval doesn't enclose the root, so it returns not a number. For a low slope, 10 to the minus 50, we find that we get a very good result, unlike what we got with the low slope at the start. Well, what happens if we have a really big root? Well, here's one that's 10 to the 307, and we get 15-digit accuracy with 50 iterations, and this is about the maximum normal. What about a moderate-sized root, 10 to the 60, 49 iterations, and we get 15 digits. What happens if we don't think that we need that much accuracy? If you're happy with 5 digits, just set t equal to 5 and see what happens. And here, after 15 iterations, we get 5 digits of accuracy. Or, if you want, you can limit the number of iterations. If we take a maximum number of iterations to be 15, we find that we get 5 digits of accuracy. If we have a small root, okay, it's not all that small, but we get 15 digits of accuracy with 52 iterations. This next problem got terrible results from the AIs, but guess what? We get 16 digits of accuracy that I asked for. I took a chance and it worked. But we can do the same problem with a bound of 10 to the minus 6, and here we end up with no significant digits, because that's exactly the kind of thing that we have with the absolute error set too small. The AIs returned a 9.53 etc. times 10 to the minus 7, which is twice my result, but they use the B minus A divided by 2. What about a fairly small root, asking for 10 significant digits? Well, here we are, 10 significant digits, 364 iterations. Or maybe we could ask for a certain number of iterations. In this case, 370. Well, it turns out with 370 iterations, we get 12 significant digits, whereas in the previous example, with 364 iterations, we only got 10. So 6 more iterations gave us 2 more digits. Or ask for 15 digits. Well, in this case, we have to take a close look because it says that f of c is equal to 0. Nevertheless, it does return 15 digits, so that's okay. The following is the example that I asked Grok about and sent it off the rails. Well, let's see how many digits I can get. If I ask for 5, it gives me 5 digits. Ask for 10, gives me 10 digits. Ask for 14, gives me 14 digits. Ask for 15, gives me 15 digits. Ask for 16, well, it still just gives me 15 digits because we hit the limit. But you'll notice that in the last one, it returned a value of f of c equals 0. If we try something other than a linear function, in this case a cubic, we see that it returned 7 digits. And when we look at it, we see that it returned because the value of the function was equal to 0. But again, we look at the computer arithmetic. We take the approximation to the root minus the root, all cubed, and that turns out to be 7.97 times 10 to the minus 109, all cubed. And if we calculate this, it turns out to be 5.06 times 10 to the minus 325, which underflows to to 0. For the next example, we try a similar problem, only in this case we're going to use a 5th degree polynomial. In this instance, it says that f of a equals f of 0 is equal to 0, and we get no digits. Of course, the reason for that is that when you evaluate 0 minus 1.2345, etc., times 10 to the minus 100, all raised to the 5th power, we end up with something far less than 5 times 10 to the minus 324. So again, we underflow to f of a equals 0. For the next example, we will try something that's getting close to the limit of small numbers, that is, the minimum normal. In this case, we find that with 1,072 iterations, we get a very good answer of 15 digits. But now, if we try another small number, 1.2345 times 10 to the minus 312, we are in what is referred to as the subnormal range, and this time, with 1,073 iterations, we get an f of c equals 0, and we get only 11 digits of accuracy, but that's to be expected because we're dealing here with a very small number. Our last example takes a look at what happens when we go from a very large negative number to a very large positive number for our interval. We try for 15 digits, and after 2,091 iterations, we get 10 significant digits, and we have f of c equals 0. That will be about the most iterations that you'll ever encounter. At this point, these are the examples I've got, so I suggest maybe you try your own problems and see how this works out for you.